Our institute is a partner in the CERAM project. They are other partners, also University of Parma in Italy. I have a long-term cooperation with Professor Gianni Nicoletto from Department of Engineering and Architecture from Parma University. And we have obtained a lot of results in last years concerning behavior of materials which are produced by additive manufacturing. And based on this, I prepared our Deposition talk. It is definitely nothing new that additive manufacturing is very quickly developing production technology, which is based on joining of materials layer upon layer or point upon point to produce and build objects from 3D models. At present, we have a lot of papers in scientific journals. We have many international conferences. We have winter schools like this, and we can find many specialized books. An example you can see here on the screen. On the left-hand side, additive manufacturing book. In the middle, 3D printing and additive manufacturing. On the right-hand side, you can see a series of books by Springer, Additive Manufacturing Technologies. Yesterday, I checked the databases Web of Science. And if you check topic additive manufacturing, for the year 20, you find 6,100 results. Even for this year, 21, we can find 295 results. It means more than 10 papers daily. If I take a little bit more specialized term, metal laser sintering, in year 20, there are 211 results. In the broader databases, Scopus, topic additive manufacturing, brings in 1920 nearly 30,000 results. And in all years, together, 135,000. So could you imagine to follow or to read all these papers? Impossible. When we speak about additive manufacturing, very often we hear about next industrial revolution. I think it is a little bit exaggerated. However, I agree that it is very interesting, very good technology, advanced technology, however, for special tasks. Let me to go a little bit to history. Additive manufacturing was patented 50 years ago in 1971. Later on was patented concept of selective laser sintering, which concerns molding processes by laser and to create 3D objects. It was patented in 1979. Very sharp acceleration of this technology, however, we can follow since the end of the 90s. It is related, or it was related to development of computer technology, naturally. It is related to friendly design software, because it is important part. Then development of interfaces to AM processes, and naturally development in laser technology and electron beam technology, because the output or power of lasers increased immensely. So these 5 items are basis for this very sharp acceleration of 3D printing of metals. As regards materials, it started with polymers. In 90s, it was focused since 90s to metals, And nowadays we are able to print also ceramics. 3D printing or additive manufacturing has obvious advantages. They are mentioned in all papers in introduction, and very nice. These advantages were listed today in the first talk by Professor Torgersen. I would repeat that manufacturing of parts can be done directly from a CAD file. It is very comfortable, and we can so make rapid prototyping. So we can change very quickly this file, and we can produce a new component. Very important is that we can build components with very complex shape with internal features. Some of them were presented also in the previous talks, very complicated components for aerospace. Very important is that this technology is connected with minimum material waste. And in the case of expensive materials, it is something. Again, it is also very suitable advantage is that we can fabricate relatively small series of products. And it means that it's not necessary to use quite expensive tools and implements and so on. So the advantages are obvious and are very often mentioned. On the other hand, there are also drawbacks and shortcomings, and they are mentioned not so often. First of all, it is a very complex technology. Problem is that there are many processing parameters which strongly influence the quality of products, the material behavior. And problem is that in many cases, if you buy a machine for 3D printing of metals, some parameters are given and you cannot change them so easily. The technology for metals, for printing of alloys, is expensive. But it is true for metals. It is not so true for plastics. Problem is rough surface finish. The surface finish is different in different orientations, and it may be a problem in the case of components with very complicated shape, with internal features, and in the case when the components are cyclically loaded, because the surface finish, if it's not well, can decrease the fatigue properties. This technology requires lots of post-processing. It means heating and heaping and so on. And these technologies are also not very cheap. Though this enormous amount of papers, publications, and so on, it is interesting that up to now, not enough knowledge and experience we have. And I think that further manufacturing skills are needed, especially in particular cases. So please, I would like to stress that especially fatigue behavior, failure criteria, and failure prediction of direct metallized or sintered materials has to be thoroughly assessed for particular cases. This morning we have heard talk about material, not metallic materials or plastics, and in our institute we have these machines which are from company Prusha. It is a Czech company, and these machines were mentioned also this morning by Professor Marasvina. They have the same machines in this institute. These machines are produced in Prague, and it is surprising that they produce 9,000 printers a month. The cost is quite low, 300 to 700 euros, so you can buy it also for your own home. You can print things like this. It is here only examples for your children. You can print dragons, you can print such spool. It is interesting that these nuts here, you cannot lose because they are, you can draw through it, but it cannot be lost. You can print for your lab shelf or test tubes or some toys. So in the case of plastics, it is very easy. However, in the case of materials, in metallic materials, it is much more complicated. I would like to speak in my talk about two materials, namely titanium 6 aluminum 4 vanadium alloys, and about the super alloy Inconel. Here you can see on the left-hand side an example of lightweight turbine cover door hinge for Airbus. You see that it is really a very complicated component, and if you want to produce such component conventionally, it is really hard task. On the other hand, this component should be completely safe. It means it should have good fatigue properties. We can predict the behavior of cracks in such component. So from this point of view, it is again not so easy to produce such component by additive manufacturing. On the right-hand side, I would like to show you an example of spinal implants. Again, complicated component. Could you imagine to do something like that by conventional technology? Additive manufacturing of metals has practically two main branches, I would say. On the left-hand side is a branch powder bed technologies. So we build components from powder, and one of most often used is laser beam melting, and among them direct metal laser sintering. It is a method I would discuss in my talk, and electron beam melting, where instead of laser is used electron beam. Then we have powder deposition technologies. It means laser engineered net shaping, direct metal laser deposition, or laser cladding. There are many other technologies, but I would like to concentrate myself on direct metal laser sintering. The method is relatively easy, and only to briefly mention, the component is placed on this building platform. In the case of direct metal laser sintering, the platform is covered by a very thin layer of powder, which is here in this container by this recoater. Then the thin layer of powder is melted by laser beam, which is coming from laser units through the scan head, which is moved by computer, and layer-wise the component is built. The building platform is decreasing. Practically the same principle was presented in the preceding talk by Professor Spagnoli for polymetric materials. So the principle is identical. In the case of metallic materials, the machines are naturally much more expensive than systems for plastics, and cost is in hundreds of thousands to millions of euros. Here you can see examples of three machines, namely Renishop A250, Sint M270, and SLM 280HL. And there are machines on which we produced our specimens for our testing. At the market, you can find today many many specialized machines. So, properties of direct metal laser sintered materials are strongly dependent on many processing parameters. It was mentioned also in the preceding talks. But I would like to stress that in the case of metallic materials, it is much more important to set precisely all parameters. We begin with input powder. The input powder has to have good quality, purity, size, and so on. Important is laser scanning strategy. It means how the laser beam is moving on the platform, on the component. This strategy may be specific for specific machines. Nowadays are even systems using 2 or more laser beams simultaneously to increase the velocity of building. Important is energy density. How much energy brings the electron or laser beam into material? Important is scan speed. How quick moves the laser beam on the material, on the powder? How quickly produces this laser, this melting pool? Also, the scan speed is important. Laser power, it increased during the last 20 years very much, and nowadays the laser power is very strong. Layer thickness, how thick is the layer we melt. Then build orientation, so in which orientation we build the component. Also, component size and shape can influence the material parameters, for example, defects in material. Important is even location on the building plate, if it is in the middle or somewhere in the corner. The question how the built platform is heated. It may be heated, maybe not, so there are also problems with, or it is also one of parameters. And naturally final heat treatment of the component. So I would like to stress, and please mention that attention to material properties and structure must be paid, because this structure is strongly dependent on many parameters which are used. At the beginning, I told you that I will speak about 2 engineering alloys which are often used, namely titanium alloy, titanium 6 aluminum for vanadium alloy, which is low weight, high strength, biocompatibility, good material with high corrosion resistance. It is used in conventional form in aerospace, in medicine, and in chemical industry. The second material, completely different, is Inconel 718 super alloy, which is material used for high temperature and cryogenic apparatus with excellent high temperature and cryogenic properties. It is used in industry, many industrial applications. The direct metal laser sintering brings problems which are mentioned here. The process is prone to porosity and defects which are arising from fusion processes and thermal stresses, scanning strategy, and so on. And this porosity and defects can strongly influence the fatigue properties. Not too much tensile properties. However, from the point of view of fatigue, it may be very important. Important is also uneven defect distribution in component. If we have in a component some place where some defects concentrate, and simultaneously this place is in a component loaded by cyclic loads, it may be dangerous. A problem is directionality of structure. It means anisotropy. This anisotropy is due to layer-wise building this material. Generally, in this technology big role play high residual stresses in component and naturally surface quality, which is dependent on the building direction and which again influences strongly the fatigue behavior of materials. Let me show some examples of microstructure of titanium alloy. On the left-hand side here, you can see the microstructure of non-optimally microstructure of material, which was produced on Renishaw AM250 machine with not optimally set parameters. You can see that the material has many defects and the average porosity is nearly 4%. Such material is naturally not very good from the point of view of fatigue behavior. On the other hand, on the right-hand side, you can see the microstructure of titanium 6 alloy with optimally set parameters. This was produced on Elsint M270 machine. The random defect distribution you can see, and the average porosity decreased to 0.25. So please remember that defects can be substantially reduced by optimization of processing parameters. Here you can see examples of defects which can appear in this microstructure. Again, it is titanium 6 aluminum alloy, and you can see here process driving effects, fusion voids, gas pores, and partially unmelted powder particles. Here are partially unmelted particles. This defect is quite large. You can see in this dimension, it makes nearly 100 microns, and it is dangerous. On the other hand, on the fatigue fracture surface, we observed a very small void on which was not dangerous from the point of view of fatigue. So often these materials are post-processed by hot isostatic pressing, and in this case we can reach density 99.8, and this is a quite good result, which is comparable with conventional-made materials. The situation in Inconel 718 is shown here. Again, the situation is very similar. Here you can see a characteristic fusion void, quite large. Here on the right-hand side, you can see the effect along the melt pool line. This is a melt pool line, and the melting was not good enough. So here is a small crack. So it is important to say that very small defects cannot be removed in the case of both materials completely. When they are very small, then from the point of view of fatigue, it is not decisive. When they are large, it is dangerous. So now to directionality of structure, anisotropy. Again, the case of titanium 6 alloy. This direction is build direction of the material. The machine used was Elsint M270 machine. The laser power was set to 200 watts, layer thickness 30 microns, and the material was stress relieved at 380 centigrades for 8 hours in air. The microstructure consists of columnar grains in the building direction, and we can see here epitaxial growth. On this plane, which is perpendicular to the build direction, you can see cross-section through these columns. So the microstructure is different in different orientations. How it looks in the case of Inconel. Inconel was produced on a Renishaw machine, another machine. Laser power was 200 watts, layer thickness larger, 50 microns, and it is as-built state. Again, you can see directionality of microstructure. Here you can see nice this laser pools, how the laser melted the material. There is also directionality in this direction, in direction of build direction, and here at this plane, which is perpendicular to the building direction, you can see again sections through these melting pools. So again here the structure exhibits directionality. Residual stresses. It is also very important topic. We know that these stresses develops due to rapid heating and cooling. And these stresses can result in deformation of the component, even in failure of component. So the program has to be done in such a way to minimize these residual stresses. They appear either within the additive process, but also in post-processing steps. It has influence on dimensional accuracy, distortions, and so on. We distinguish residual stresses according to 3 types, namely type 1, type 2, and type 3. Type 1 are macro-scale stresses. They are most important, and they can change dimensions or distortions of the component. Type 2 are microscale. They are stresses between individual grains. So they can then influence, for example, fatigue initiation and mechanisms of damage. And type 3 are sub-microscale stresses inside grains, and they influence movement of dislocations. And finally, they can influence, for example, the behavior of the plastic zone in the case of fatigue cracks when they propagate very slowly. So all these 3 types of residual stresses can influence the fatigue behavior of materials. Here I would like to show you specimens which we prepared for our testing of titanium 6 alloy. Build direction in the first case here on the top was in this direction, and in the second case below the building direction was perpendicular to the screen. The specimens were removed from the platform, from the building platform, in this case without any stress relieving, simply by cutting of the supports which were here, and in this case here. And what we can see, in this case, the specimen is practically heavily deformed, not in this case. So these residual stresses are very strong, and stress relieving is a necessary post-processing step. The last moment is surface quality, which is dependent on the building direction. Here you can see an example of surface of titanium 6 alloy, and you can see that the surface strongly depends on building orientation. This material was built on L-Synth and 290 machine with 400 watt laser power. The layer thickness was set to 60 micrometers, and the scanning strategy was defined by company BMIT. It is Italian company we cooperated with, and the scanning strategy is often developed or is prescribed by the company, and it is not commonly known sometimes. Yeah? The powder which was used for the component is shown here. You can see that there are particles of different diameter. The average particle size is nearly 30 to 34 microns. The surface of the component, which is perpendicular to the build direction, it means this surface on the left-hand side, is relatively smooth. Here you can see traces of the laser, of these laser pools, how the laser moved, and the surface quality is relatively good. On the right-hand side, you can see the lateral surface. This is build direction here. And we can see that they are not fully solved, particles, melted particles, which are attached to the surface. So the surface is strongly dependent on the orientation. An example of a specimen for tests, for fatigue tests, which was built in an as-built surface, is shown here. You can see here the traces of the last layer, this strategy. Naturally, such surface should be somehow improved. And for example, for components which are used for healing of implants for human pelvis, you can see here it is a symphysis collapse, and surface of such component has to be improved. Namely, in this case, the improvement was made by short pinning. Nevertheless, you can see that the surface is not completely flat. The situation, once more, is shown here in the case of Inconel 780. This material was prepared on Renishaw 250 machines. The laser power was set to 200 watts. The layer thickness was 30 microns. And again, the scanning strategy was developed in company BMIT. The powder particle size was 20 to 50 microns. You can see these particles here. This distribution of these particles, the size is much more better than in the preceding case. The chemical composition of this alloy is shown here. So you can see it is predominantly nickel, chromium 20%, niobium 5%, some titanium, molybdenum. And rest is the ferrum. Here you can see the fracture surfaces of components which were, or fracture specimens which were loaded in tension compression. This is fracture surface, and this is surface which is the upper surface. It means build direction was in this direction. This is build direction, and it is upper surface. You see that this upper surface is nice, flat. The crack started somehow here and propagated in this direction. The lateral side of the specimen you can see here, and if the crack started on the lateral side, there are many problems with notches here. You can see here unmelted particles. So such surface is, from the point of view of initiation of cracks, much worse than this one. So the as-built surface roughness strongly depends on the orientation. So please remember this statement. So let me now conclude that fatigue properties of direct metal laser sintered materials strongly depends on defects and their distribution, on homogeneity or inhomogeneity and directionality of microstructure, depends on residual stresses and microstresses, and naturally on surface roughness. It means that all these parameters strongly influence fatigue strength and fatigue limit, and influence also long fatigue growth and threshold values. I would like in the next part to show you some concrete results which we obtained on materials produced by direct metal laser sintering. Let us start with titanium 6 alloy. We have prepared or built specimens for plane bending. You can see here an example of such specimens. The specimens were built on LSINT M270 machine with 200 watt laser power. Again, the layer thickness was nearly 30 microns, and the multi-directional scan strategy was chosen. It means that the scan direction rotated in the preceding layer on some angle. And finally, the material was stress relieved at 380 centigrades for 8 hours in air. So we prepared 3 types of specimens with 3 orientations. It is shown here. The first case, which is denoted as A, means that the specimen is loaded in such a way that the crack initiates on this surface and then propagates across the layers in this way. So it propagates in opposite to the build direction. It is the same. The case B, it is this case, means that the crack initiates on this surface and propagates again, also across the layers. However, the crack plane is parallel to the build direction. And the third case is when the crack starts on this plane and is propagating along the layers. It is a case C. And now how it influences the fatigue behavior. Here you can see SM or so-called Wheeler curves, which is a dependence of the stress amplitude, better to say, the dependence of number of cycles on the stress amplitudes. So you can see that for the case A, when the crack is propagating across, the full points show the fatigue strength. So for, let us say, 250 megapascal, the specimen fails after 2 times 10 to 5 cycles. You can see that the behavior of orientation A and B is nearly the same. The scatter is natural because the surface is rough and it does play a role. And you can see that worst orientation is this orientation C. It means when the crack propagates along the or starts on the surface and propagates along the layers. The difference is quite large. For example, here, if the loading would be, for example, of a component for treating of human pelvis, let us say 120 megapascals. So after 10 to 5 cycles, the component will fail. However, if the orientation is A or C, the specimen will survive. So I would like to conclude that fatigue performance depends on the build orientation strongly, and in this case, the lowest fatigue strengths exhibit orientation C. Once more to show the situation. So when it is build direction, when the crack starts here, initiate here, so propagates practically through this material, through the structure, the lifetime is worst. Now, I would like to show you results on completely different material, namely Inconel 718. This material was manufactured on another machine named Renishaw 250. The laser power was nearly 200 watts, and the layer thickness was 30 microns. Again, the scanning strategy was BMID strategy. The heat treatment in this case was the following: 970 centigrades for 1 hour, then cooling in argon, then age hardening at 710 centigrades for 8 hours, and then 610 centigrades for 8 hours. It means quite complicated heat treatment. And again, SN curves or results. And you can see that for pure plane bending, the result is very, very similar. Again, orientation A and B is better than orientation C. So it depends on the quality of the surface predominantly, and this has to be simply taken into account. If you imagine a component with internal features, which is loaded by cyclic loads, it can play a role because the lifetime can change 1 order of magnitude. Here you can see fracture surfaces of specimens, which was presented here. And on the left-hand side, you can see this relatively flat surface, higher fatigue life. The crack started somewhere here and propagated in this direction. On the left-hand side, orientation C with not so nice surface, lower fatigue life, and the crack initiation site was nearly in this region. So surface roughness determines the fatigue life naturally when internal defects are minimized by optimization of fatigue processing parameters. Once more, I repeat that to remove defects, internal defects completely is practically impossible. So the next thing is problem of propagation of long fatigue cracks. Just a moment, something. Yes, okay. Propagation of long fatigue cracks. It is also important because if you have a component, for example, for aircraft industry, there are often cracks in such components. Airplanes are flying with cracks, and we have to say, okay, such crack is okay. This component has to be changed. So we have to know how fatigue cracks propagate in materials. We have prepared 3 types of Ct specimens. There are specimens where the crack is initiated by cyclic loads from this notch, and then the crack is propagating in this direction, and we measure the fatigue crack growth of this curve. We have prepared 3 types of specimen again. The type 1 or type A is a type when the crack growth is perpendicular to layers. It is this one. Then the crack B is crack growth is perpendicular to layers and in plane parallel to build direction. And the case C, the crack growth is along the layers in this way, perpendicular to build direction. We have performed tests on Royal Amsler resonant testing systems. The frequency of loading was between 60 and 80 Hertz. Experiments were done at room temperature in air. The cracks were, in our case, determined by optical measurements by microscope or CCD cameras. And the measurement was done according to ASTM standard, which prescribes the conditions of testing. Let me to say some words about microstructure. I told you that the S-built specimen has to be somehow treated by temperature treatment, heat treatment. This material was prepared on LSynth M270 machine. The laser power was nearly 200 watts and laser thickness was 50 microns. The laser speed was 0.8 meter per second. And again, the scanning strategy was developed by BMID. The stress relieving was done at 380 centigrades for 8 hours in argon. Our aim was to study the influence of heat treatment on fatigue crack growth. Some words to the microstructure of this material. Here you can see the microstructure on the plane which is parallel to build direction. You can see primary columnar beta grains which are elongated in this direction. On the plane which is perpendicular to the build direction, this is this plane, we can see again columnar structure, and these columns are seen as these circles on this plane. At higher magnification, we can see that this microstructure is relatively homogeneous, and it is typical fine acicular alpha prime martensite structure. This structure is only slightly different from the microstructure of the as-built specimen. If you perform a study of microstructure on as-built specimen and this specimen, and if you mix your photos, you are perhaps not able to distinguish. So microstructure similar to that of built specimen. And now to the propagation of long fatigue cracks. This is a dependence, experimentally determined dependence of the crack growth rate, which is given in millimeters per cycle, from 10 to minus 7 to 10 to minus 4 millimeter per cycle, on the stress intensity factor range. Stress intensity factor range is a quantity which is characterizing the loading of the crack, and according to this we can simply compare different cases. So you can see first of all that the experimental data exhibit a very large scatter. And secondly, there is no apparent influence of building direction. Orientation A, B, and C in one broad scatter band. Only to mention, the loading was done at R ratio 0.1. It means that the minimum to maximum load was 0.1. Now let me to compare this data with as-built material. Here you can see our data, but only the orientation C in this case, after stress relieving 380, and compared with as-built material. These data were taken from literature, from paper by Loyders and paper by Becker. You can see that their scatter was also very high. However, the curve for as-built material is shifted to the left. It means to higher crack growth rate. So for the same loading, let us say 6 megapascal meter to 1/2, the difference is nearly 1 order or more of magnitude. So here the propagation is much more quicker. The main problem is, however, in the threshold values. So the threshold for crack propagation in the as-built material is shifted towards very low values, nearly 1.3 megapascal meter to 1/2. What does it mean? When I have a small crack in material, in this as-built material, it propagates much more easier than in this case. So we can see that only the stress relieving resulted in improvement of material, of as-built material. What may be the reason? Maybe residual stresses, because the stress relieving is done usually at this temperature. So we performed an experiment and we measured the residual stresses in our specimen. You can see Ct specimen, and we measured it in 2 directions, longitudinal and transversal. We have used X-ray sinus quadrat psi method, and we determined the stresses on a surface which was electrolytically polished and then electrolytically removed nearly 0.1 millimeter, because if you only polish the surface, you can produce residual stresses. So we were surprised that after this heating, stress relieving, really the residual stresses were extremely low. We found only in the T direction 2 megapascal, and shear stress minus 2 megapascal is nothing. And in longitudinal direction, only 28 or 6, it is really nothing. So it means that the heat treatment at 300 centigrade removes long range residual stresses, which is good. It means that the component is not deformed then if we remove it from the platform. And simultaneously, it seems that to explain this shift by means of residual stresses, which was done in literature, is perhaps not okay. It seems that long-range residual stresses seem to not be responsible for the high scatter of data. And it means that the details of crack growth mechanism should be in this material further investigated. It is a little bit open question now. So let me to show you results on the same material produced on another machine, namely Elsint M290, with 400 watt laser power. Laser beam diameter was 70 microns. Layer thickness was 60 microns. The material after production was heat treated at 900 centigrades for 2 hours, and then cooled to 520 in air, and then to room temperature. Again, the microstructure, excuse me. This is build direction. You can see again columnar microstructure and elongated structure, not so pronounced as in the case at 380. Similar situation on the section by plane perpendicular to wheel direction, and at higher magnification we can observe here a little bit coarser microstructure, lamellas of alpha plus beta faces. Locally we can find here coarse alpha grains, and the material is generally somewhat softer. So here is no expressed directionality of microstructure. We have again measured the crack propagation curve, which is dependence of crack growth rate on the stress intensity factor range. And what we can see, all orientations A, B, and C, or points, lie on one curve. The scatter is relatively small, like in conventional materials. The scatter is small, and if we compare now data at 380 and 900, so we can say that this curve can be fitted quite well with these two curves, and the threshold value, it means the value below which the long crack does not propagate, is 3.5 megapascal meter to 1/2 for 380, and practically the same for 900. So here is only reduced scatter of experimental data. And now please, we can compare, no, just a moment, yes. Now I would like to show you the fracture surfaces. At 380, the fatty crack propagates practically in the threshold region, so it means in the region where the crack growth is very slow, through the microstructure. So the crack profile is very flat, and the fracture surface doesn't exhibit special features. So there is no apparent influence of columnar grains on the crack growth. The crack propagates in this case at 380 at this low rate by cyclic damage of fine alpha pi martensite structure. In the case of heat treatment 900, again, the fracture profile is here. The crack is again flat and is running through the microstructure. However, in the case of threshold region here, so crack growth rate very low, 10 to minus 8 millimeter per cycle, the mechanism is somewhat different. You can see here these flat areas. So the crack growth mechanism consists in cyclic damage of fine alpha pi martensite acicular structure at 380, and it changed to damage of fine lamellar alpha plus beta structure at 900 centigrades. Nevertheless, there is practically no influence on the threshold values, so the mechanism seems to be a little bit different. And now let me to compare our data, it means measurement on our specimens with material which is manufactured conventionally. There are data by Boyce and Ricci and Oguma, this red and green points. What we can see, our material is practically the same, somewhat worse here in this area than the conventional material. So it means if we set very well parameters of 3D printing, very well heat treating, so we can reach material which is comparable to the conventional produced material. And now let me to say some words about the influence of asymmetry of loading. It is also important because some components are often loaded with high mean stresses and small cyclic amplitudes. This is characterized by R ratio, which is minimum to maximum loading in a cycle, R equals 0.8. And we can see that for titanium 6 alloy, there is no influence of orientation. Again, a nice curve can be described by this equation, and the threshold value is 2 megapascal meter to 1/2. It is a much lower value than in the case of R equals 0.1. Now, what is the difference? Let us see this area of high growth rates. The fracture surface of both cases is here. R equals 0.1 is here, R equals 0.8 is here. So in Paris region, it means for these high rates, the fracture surface is practically similar, and it means that the crack growth mechanism is practically the same in both cases, so if the mean stress is high or not. What about the threshold region here, where the influence of R ratio is so strong? We can see again two examples of the fracture surfaces. Here, for R equals 0.1, we can see that the damage takes place along boundaries of lamellas. The fracture surface is very complicated. On the other hand, for R equals 0.8, you can see that there is a damage by brittle cracking of lamellas. So the crack is propagating perhaps slowly and then jump, propagating slowly and jump. And it is related to the microstructure. So we have observed different crack growth mechanism in the case of threshold region. Maybe that if the procedure of 3D building can change the microstructure, maybe this effect may be smaller, but it's a question. So now let me to say briefly some words about behavior of superior Inconel 718. Again, we have prepared such CT specimens. In this case, we studied only proper crack propagation in this direction, build direction. Specimens were prepared on Renishaw machine with 200-watt laser power. Layer thickness was 50 microns. Raster fashion was 50 to 50 microns point to point. The point exposure was 250 microseconds. Scanning speed 200 millimeters per second. Lateral space between lines 180 millimeters. You can see that there are many parameters which can be changed. And the fatigue testing was performed again on our Royal resonance testing pulsator. Some words to microstructure. You can see that the microstructure of as-built material is really complicated. On the right-hand side, you can see that there are strong features of local solidification. So here you can see these melting pools, this section shows these pools. You can see fine columnar microdendritic regions, for example, here in this region. You can see here, for example, gamma prime, gamma 2 prime, cuboidal or elongated precipitates in gamma matrix. So the microstructure is extremely complicated. It is important to say that it is similar in all directions in this case. And here are results of the measurement of crack growth on the stress intensity factor amplitude. What we can see is that the scatter data is not so bad. We can fit the experimental data by this equation, and the threshold value is nearly 3 megapascal meter to 1/2. But now, if we here I would like to show you the crack growth, the fatigue fracture surface. It is a crack growth direction here. You can see that crack is running through this microstructure, and there is any specific interference with grain boundaries, melting pools, or so on. Simply, the crack is running through this microstructure and is practically governed by the finest features of this microstructure. As regards the fatigue fracture surface, so for near threshold region, where the delta K is only 4 and the crack growth rate is low, we can see on the fracture surface that the mechanism of growth in this case is based on planar cyclic slip. Damage takes place mainly in slip bands. It is derived from other observations of microstructure of this material. I am not showing this data here. And we can observe formation of microcracks and linking of microcracks to the main crack. It is a mechanism of crack growth in this material at low crack growth rates. On the other hand, in the Paris region, for delta K, 10 megapascal, where the crack growth rate is nearly 10 to minus 5 millimeter per cycle, you can see that the fracture surface is much coarser, but similar a little bit to this in threshold region. However, in the region of very high rates, so for delta K 30 and the crack growth rate 10 to minus 4 millimeter per cycle, we can see that there is a larger extent of cyclic plasticity, more opened and larger secondary cracks. It can be seen here, yes. And we can even observe formation of striations. It means it is a cycle for cycle makes these striations. So it is very similar to the behavior of conventional produced material. And now, if we compare our data on material produced, Inconel produced by selective laser melting, this curve, with conventional data, and I compare it with very old data published nearly 50 years ago on conventional material, so we can see there is a big difference. Practically, the same behavior we have here for the highest rates, because the mechanism of crack growth by means of this striation and so on is identical. However, in the threshold values, this material produced by thermal technology is definitely much worse. So I can conclude that crack growth resistance for delta K threshold above 20 megapascal corresponds to the conventionally manufactured alloy, and low threshold is related to very fine microstructure, and the material behavior is much worse. So there is a space for improvement of technology, and maybe that it can be changed in such a way that the material behavior would reach the behavior of conventional made material. So my last part of presentation is focused on the influence of pre-deformation on fatigue life of titanium 6 alloy, which is used for implants. We have cooperated with a company which is developing implants for treatment of human pelvis. They are new developments of implants, and these implants are in a human body cyclically loaded. When you go, so the loadings on the pelvis are quite high, and we need to have smallest dimensions and the highest fatigue behavior. So here you can see a pelvis which is treated by this implant. It is here, the symphysis region, and we have cycled this pelvis treated with this implant in a cyclic machine, and we observed how this implant behaves. We have prepared also specimens for tensile tests, and these specimens were heat treated at 950 for 2 hours, and the surface was treated by corundum power blasting and ballotining. It is the same as is used for these implants. And now we wanted to determine the fatigue life curves, ascent curves, for undeformed specimens and pre-deformed specimens. The reason was simple. If you apply this implant to the pelvis for here, in the procedure, this is slightly bent during surgery. These parts are bent. And now there is a question. In the case of conventional steels, it doesn't play a role. How it is in the case of implants which are printed. So we pre-deformed specimens to 2% plastic strain and we formed ascent curves. It is a dependence against number of cycles to cycle on the stress amplitude, and again for the loading with R01. The fatigue limit is here nearly 160 megapascal. It is based on 10 to 6 cycles. These points are specimens which failed, unfailed specimens are here. And now, if we compare it with pre-deformed specimens, the lifetime is substantially lower, and even here we go below the fatigue limit for so small plastic deformation of this material. So it is very important result, and it means that during this small deformation, plastic deformation, since the beginning, in the surface layer, cracks appear, and these cracks can then propagate very easily and result in very low fatigue limit. So to increase the fatigue strength, surface finishing of critical regions of components is necessary. So in our case, it means that these areas which are bent by the application of this implant should be polished in sufficient way. So, ladies and gentlemen, I was perhaps a little bit longer. I apologize, and let me to conclude my talk. So, I would like to conclude that fatigue behavior of direct metal laser sintered engineering alloys is strongly dependent on many processing parameters. It is nothing new, but nevertheless, it has to be in mind. To get materials with good fatigue strength and good crack growth resistivity, it is necessary to set optimal processing parameters and to use post-processing procedures, which is not easy task. And to guarantee the fatigue properties of direct metal laser sintered materials, fatigue and microstructure tests has to be performed for the applied processing parameters and post-processing treatment. So thank you very much, and that's all from me. Thank you.
Thank you very much, Professor Kunz, for your very interesting presentation. If there are any questions.
My name, I think I have something. My name is Angel Cernescu. So I have a question related to fatigue behavior and compared to fatigue crack propagation. That
Yes.
there is no, I've seen, in case of fatigue behavior, there is the influence of the crack initiation because compared to fatigue crack propagation, because I've seen, so in the fatigue behavior, you showed us that only if the crack is growing between the layers,
Yeah.
there is a lower fatigue durability, fatigue life.
Exactly.
But instead of fatigue crack grow, there is no influence on the microstructure.
Yes.
Why there is no influence of microstructure in the case of propagation or long crack propagation, and there is influence when the crack is growing, is initiated?
Yeah. Just a moment. It's here. Yeah. So
yes,
the whole lifetime. Yes, the whole lifetime is given by changes of mechanical properties during cycling. It is the first stage. Then by crack initiation, and then by crack propagation. And here, if I have a total life, so it is a sum of all these effects. Yes. So here, in this case, it is given predominantly by initiation of cracks, and the crack propagation practically plays a very small role. On the other hand, if you have in a component very long crack, let us say 10 millimeters. So here, the problem of crack growth is very important, and especially the threshold values. Okay.
Yes. And also the threshold value is dependent by the microstructure, I've seen.
Yes, the threshold value depends on the microstructure, because the crack propagates by processes in the plastic zone. And you could imagine that if the microstructure is different, so the processes in plastic zone are different. For example, in this Inconel, there is a tendency to build a long fatigue bands, and it depends then on the movement of dislocations and so on. So the microstructure critically influences the threshold values.
And once the crack is initiated, when the crack is growing, then there is no more influence of the microstructure in long crack propagation.
It depends on material and on the structure, definitely. I showed you only two cases, yes, here.
Yes.
Inconel and titanium alloy.
Titanium, yes. And I've seen that there is, in the Paris domain, there is influence of microstructure only, you showed us, only in case of Inconel.
Yes, it was which one? Yes, the influence in Paris region was relatively small. Yes.
Yes.
It is where it is this comparison. No. Excuse me, I cannot find it. Too many. Here, yes. So it is practically the same, the material produced, manufactured conventionally, and our material.
Yes. Okay, thank you very much for discussion.
Thank you.
Okay. So I think the main point is that we need to take into account that for titanium 6, for the fatigue strength as built material, it's around 700, 600, 700 megapascals. And here it's only 150. I think this is the main point here. So to be careful when we design and use additive manufactured components to take care on fatigue.
Exactly. I wanted to say that many parameters which are set for this production can strongly influence the fatigue parameters. It is not the case of, for example, tensile properties. There is the influence much more weaker. However, in the case of fatigue, it has to be taken into account, and really it is important to test material from the point of view of defects, from the point of view of microstructure, simply to be careful.
Okay, there are...
Sorry.
Yes, please.
May I ask a question, please?
Yes.
I'm Mattia from Parma. Thank you so much, Professor Kunz, for your interesting presentation. Just a curiosity, you have mentioned several times a so-called scanning strategy developed by BMIT.
Yeah.
So what do you mean for scanning strategy? Are you referring to some process parameters involved in the printing process?
No, frankly speaking, we have only data from this company, and it was at the time a little bit secret how to scan the material. So we said, okay, it is strategy was developed here, and in cooperation with them, we prepare this material. So I think that generally this may be a problem of knowledge, yes. And if it's a company, the company is not ready to say knowledge.
Okay, thank you so much.
I know that there are systems where you can also in your institute change the parameters and so on, and to study this in detail, but it was not our case. Our case was simply to take material which was prepared for conventional cases and to check the material properties.
Okay, thank you so much.
Thank you. Gianni Nicoletto is maybe more informed.
Okay, there are any other questions for Professor Kunz? If not, thank you very much for your presentation and for your contribution to the winter school. So the next one will be organized by your institute in Brno, or maybe also online, depends on the pandemic situation.
I think there was someone who tried to ask something.
Yes, I have a question. Can you hear me?
Yeah.
Okay, this is Bilkay. I'm from Turkey, and I work on jet engines, mostly design, and I'm very interested in the additive manufactured parts. Thank you very much for your presentation. Yeah. I have two questions. The first one is, have you done any surface finishing with the specimens, or these are like as-built, just out of the additive manufacturing machines?
As built. Now we are performing experiments where we polish our specimens. Exactly here, just a moment, if you see my presentation, we are now playing with surface finishing of these parts on these symphysis slabs. We try to have material which is as-built material after ballotining, material which is polished in conventional ways. And we would like to measure the fatigue behavior of material to say then it is possible or not to use this procedure for polishing. Naturally, if you polish the material very well, so you can reach better results.
Okay. And the second question is like, have you done any high temperature fatigue experiments?
Up to now, not at this material. In the institute, we are able to perform experiments up to very high temperatures, but we didn't perform experiments on this 3D printed alloys up to now.
Okay, thank you very much.
Okay. Thank you very much, Professor Kunz. I think we can close your lecture.
Thank you for the invitation. Bye-bye.
Bye.